Good afternoon again. It's October, not September, October 20th, 2025. Kelly 1022, Telecommunications, Venture College. All right, so today we're going to tackle or begin tackling the amplitude modulation. We got some stuff to cover. And okay, I'm just going to get here. Participants, it's just on my screen here. All right, so I got the chat screen on in private here, participants, and we have on the main display, and we have the PowerPoint. So, one more thing. Before Thursday, just make sure that you have everything. It looks like everybody has done everything, except I can see some of us still haven't done the test. So please do this before it runs out, and it runs out. When does it run out? October 23rd. Okay. 11:59 p.m. Make sure you do that. Okay. All right. Minimize this window and press F5 to start. Well, we have to start. Before we start, I'm going to do a bit of a prelude. Where is my board? Here's my board. All right. So, just going to start with this thing here. If we have a couple of frequencies together, let's say one is going to be, well, let's call it very high. And the other one is going to be quite low comparing to the very high one. All right. So let's say here we have the, straight line here. Frequencies. Here's a frequency. And over here, we're going to have some sort of a whatever magnitude of that, not as straight as the other one. Okay. So let's say we have, 1,000 hertz here. 1, 2, 3. And that is going to be in hertz. All right. So we have a frequency of 1,000 hertz, and into the amplifier or the mixer. Mixer will be a device that mixes two frequencies. And so one frequency, we're going to have 1,000 hertz, 1 kilohertz. And the other one is we're going to have, let's say, just to make things simple, let's say we're going to have 10 hertz. Right? 10. Right? If we input those two frequencies into a mixer, I'm just going to call it MX for mixer. These two frequencies are coming in, and we have one output coming out. What are we going to have on the output? Well, we're going to have some sort of a magnitude of whatever it is. Could be watts, could be volts. This doesn't matter. We're going to have that frequency present. We're going to have also the sum of those two frequencies. So this is going to be 1010 hertz right here. And we're going to have 990 hertz because we're going to have the difference. 990 hertz. Okay. Erase this here. My pen. 990 hertz right here. Here's 1,000, here's 1,010, and here's a 990. What else are we going to have present on the output? Any ideas? Because that's not the only thing that we're going to have. Harmonics. Yes, we're going to have some harmonics that are going to be, let me just get a different color here. Just to distinguish that these are the harmonics. So we're going to have harmonic here, whatever else we're going to have. What else are we going to have? I'm looking for two more things, or 2.5 things. Noise. Good. We're going to have some sort of a noise floor going on. What else? Missing one thing, one thing for sure. All right. What about this one right here? Is that going to be present? Yes, it is going to be present. So let's put that on. Somewhere here, we're going to have also that, I'm just going to make a thicker line so it can be seen. We're going to have that 10 hertz also. Quite far over there. Plus, well, these are the main things that we can expect to have. Also, we're going to have maybe there's going to be some additional noise, except from additional from the white noise that is just present. We're going to get some noise that is introduced by the electronic components that make up the mixer, because that is made from something. So we do have a lot of things that we're going to have. Now, if this main carrier frequency, well, I'm getting ahead of myself. The big frequency here, if it's a sine wave, high frequency sine wave, and the intelligence is also a sine wave. Actually, this one here is going to look a little bit different. This is going to look more like this. Something like that. Very tight sine wave of the same magnitude, all right? It's going to be just like that. Comparing to this one here. So if that was a sine wave, then we're going to have frequency present. And if this was a pure sine wave, with maybe some harmonics, because we will have harmonics of this high frequency, we will also have some harmonics of that frequency. Excuse me. And what if this is not a sine wave. Let's say this, we keep that as a pure sine wave. I didn't draw it purely because that's what we would probably see on the scope, but they would be kind of equal on top and the bottom. Well, if this is not a sine wave, what if we connect a microphone to it, and there's going to be somebody talking here to the microphone? Are we going to have a sine wave? No, this is going to look like that, all right? And is there going to be only one frequency present in there? No, we're going to have a lot of frequencies present. What if there's some music or wind blowing or the seashore noise? We're going to have all kinds of frequencies there. So in this case, are we going to have those two spikes like that? No, we're not going to have those two spikes like that. We're going to have something more. We're going to have a lot of frequencies present here and a lot of frequencies present here, and these two are going to be equal to each other. I just drew it that way. And there are going to be sums and differences between of the main big frequency plus all the frequencies and each and every one that is going to add and subtract from it. So we're going to have something that's called sidebands. All right. In telecommunications, we can use this to transmit things over a distance. If this here, this frequency is being transmitted from someplace through some sort of a link, it could be copper, air, or fiber. It gets from something, some amplifier, it gets to an input of another amplifier. Then we are going to, if this here, the input of the receiving amplifier is tuned to this frequency here, that is being presented by the output of this transmitting amplifier or the source, then we can enclose a message here. And if that is going to be tuned to the something that's called a carrier frequency, because it carries the message, it's the foundation for the message has to hang on to something, so that message hangs on to the carrier of the system, then we could have a communication. We can receive that intelligence signal, which would be the someone talking or music or whatever noise, as like seashore noise or wind blowing or birds singing. Okay. Then all we have to do is tune to this frequency, to the carrier frequency, and at the demodulating stage of the receiver, all we have to do is strip away the carrier, because we don't need that anymore at further stages, and just keep the intelligence signal. So we have a voice coming in here, and the voice is going to meet the carrier, and it's going to alter the carrier, is going to affect the carrier in a certain way, and we're going to call that modulating. So it's going to modulate the carrier. The intelligence signal is going to modulate the carrier signal. the receiver is going to listen to the carrier signal, and the carrier is also going to contain, or is going to be a modulated carrier. So the information that's coming in here is going to contain carrier and the intelligence, and further stages, whatever it is here, we're going to strip away the carrier, just keep the intelligence. And we also have, so we have a voice here, voice box, and we have a voice coming out here. Well, you're listening to that a lot, driving your car and tuning to your radio. What problems could be associated with that? Well, over the air, we could have many amplifiers here, or many transmitters that are going to transmit certain carriers. Let's say this one is going to transmit the carrier here. And it's going to have sidebands bigger than the noise. Right? And if it's over the air, if that receiver tunes to the carrier of this transmission, then it's going to ignore out of the air, it's going to ignore that one. And it's going to listen to this intelligence. So this would be a different radio station. And those things can go that way, or they can go that way. You can have many stations. And the challenge is to have those sidebands wide enough with the bandwidth so they can carry the music, for example, and the music can be not annoying, or it can have enough bandwidth to carry human voice, which we would need much less bandwidth in those sidebands. And those two sidebands, they have to be far away from each other. And those here, stations, they have to be separated far away from each other so they don't overlap. So we don't cause intermodulation or intermod. And of course, the whole system within the electronics and the components and things are designed, the way things are designed within the mixing or transmission and receiving stages, they just cannot have noise that is close to the intelligence or the carrier, because it would start interfering. And of course, in this case, the system has to be not affected by outside. It has to be immune to the outside interference, such as the power lines, fluorescent lights, any kind of machinery, and so on. Well, with AM modulation, because if this has a certain amount of amplitude, and this has certain amount of amplitude, this amplitude is constant. This one doesn't change. The carrier has a constant amplitude. This one changes. It is going to, by the varying of the amplitude of the intelligence signal, we're going to vary the magnitude that this thing is going to, in the ways of upwards and downwards, it is going to be affected. So at some point, if the volume or the amplitude of this signal is higher, then things are going to add. Yeah. Things are going to add. And if the amplitude is lower than the amplitude of the carrier signal, then it is going to weaken that. carrier signal. And it is going to go like that. And it is going to go like that. And the carrier is going to be present all the way through, except the amplitude of the carrier is going to be affected. And look, over here we have the intelligence signal. All right. So that's why we're calling this, we are modulating the carrier signal by varying the amplitude, and that is going to give us the strength of the signal. So we can hear things louder or quieter if it's an audio transmission. And of course, how fast this thing is changing, whatever the frequency is, this here can be wider or narrower, that envelope. It's got this here, all this right here and right here, and the carrier in between. That's called envelope. The envelope can shrink or expand in frequency, but it can only go so far, and it has to be regulated so the stations do not overlap each other. So the frequency of how fast things are happening here are going to affect the envelope like this. So if this is a sine wave, it's going to look like this. If it's not a sine wave, let's say it's a human voice, it is not going to look as clean as that. It's just going to look like a constantly changing something that looks like a mess, but it isn't. So here's the idea. The constant amplitude of this carrier signal, all right, that's a sine wave here, is being affected by something that's called the intelligence signal. We both shoot them to the mixer. The mixer mixes them together and shoots out the outcome of those two being combined. So that's why we call this thing amplitude modulation, because the frequency is not being changed of the carrier. The frequency of the carrier is constant. The amplitude of the carrier is constant when it goes into the mixer. And at the mixer, the amplitude of the carrier is going to be affected by this additional waveform that comes here. And how far up and down is going to swing out, and how often is going to be altered, or whatever the frequency or multiple frequencies or infinite number of frequencies are going to be present, it is going to affect the shape of the envelope sideways, which is not going to look as clean as it is if it were a sine wave. That would be the intelligence signal. Okay? So in a nutshell, that is the idea that we're going to tackle today. So we're talking about amplitude modulation. All right. Let's do some reading here. Put my laser on. Modulation involves combining an information signal with much higher sine wave frequency of a constant amplitude, which is basically what I just showed you 5 seconds ago. So again, the modulation involves combining information signal or intelligence signal with much higher sine wave frequency, and that much higher sine wave frequency is of a constant amplitude, which when it goes into the mixer. For amplitude modulation, the higher frequency sine wave is also referred as a carrier, and it does have a constant frequency. Can we modulate that carrier as far as frequency with a frequency? Yes, you can, but that is going to be called a frequency modulation, FM, which we will talk about further down the road as we continue with this class. But today we're going to concentrate on the amplitude modulation. This interaction between the information or the intelligence signal and the carrier signal is called mixing. Okay, got it. Amplitude modulation is one of the simplest forms of modulation, and it continues to be used for many applications as both the generation and the detection or demodulation do not require complex circuitry. Well, there's a give and take. You pay for that simplicity with with quality. That's why if you want to listen to the music, to some music, quality music, well, up to some certain point, then you would choose the FM radio over the AM radio. That's why on the AM radio, mostly you're going to have talk shows and some music. But the music is not going to sound as good as it would sound if we were using the frequency modulation. We'll talk about that later. Not today, though. Amplitude modulation is one of the with amplitude modulation, we will be changing the value of the peak voltage in accordance to the information signal. So the intelligence signal is going to be louder or quieter. Okay? And the instantaneous value, and it's just some math here. The instantaneous value at any given point, that's basically here's a sine wave formula here. The peak voltage times sine of the angular velocity. Well, it basically that's with time, we're going to find ourselves at certain point of a circle. That's going to be the other way. At certain point, if we go and stop, that's the one that we want to use. So that would be the angular velocity plus, well, phase shift, but we're not going to worry about that phase shift right now, but it is there. But in our case right now, we're going to just consider all that as zero. However, if you want to have the full formula for that, for the sine wave and instantaneous value, sometimes there is going to be some phase shift. So the phase shift is, or the phase angle, phase shift is going to be included in the formula. Yeah. All right. Double sideband. Double sideband. Double sideband. Here is let someone pick it up. All right. Okay, so here is a sideband because we have many frequencies when it comes to voice. So it's not that just single spike, it's a band, sideband, or certain area that requires certain bandwidth. And all the sums are going to create, sums of all the frequencies present are going to create upper sideband on this side, and all the differences are going to create lower sideband. So here's an upper sideband, and here's a lower sideband. And by the way, where's my thing here? We need to also include a couple of terms. Why pan? Here. Oh, I'm gonna write it here. RFI and EMI. Those two terms. They're both interference. That I stands for interference. This bottom one stands for electromagnetic interference. That's the outside elements. Car drives by with bad ignition. A fluorescent light is close by, somewhere close by the link. Lightning hit, and so on. Power lines. That's the sort of like a pseudo-natural interference. And there's also the other interference that we distinguish here is the radio frequency interference. Radio frequency interference would happen if there would be another transmitter close by and the carrier frequency would be too close to one of those channels. Because from here to here, we could just say it's a channel, and those channels are being regulated. The channeling of the frequencies, the broadband, or the spectrum, the usage of the spectrum is regulated by Industry Canada in Canada. And of course, because radio is, doesn't know borders, and countries talk to each other just to make sure that nobody interferes and everybody's happy. So the radio interference would be created by another radio signal producing device that will be too close and starts interfering with whatever it is being transmitted. RFI, EMI. Radio frequency interference, electromagnetic interference. All right. So there are several forms of amplitude modulation, but the most common is the double sideband or full carrier amplitude modulation. I'm going to bring that back again here. Over here in this carrier, you have the bandwidth from here to here. So you could transmit some sort of, mediocre quality music. But if you're transmitting only voice, then you can eliminate one of the sidebands. If you eliminate the lower sideband and you are transmitting only up, using filters, and you're only transmitting the upper sideband, and the upper sideband could have enough bandwidth to carry human voice, then you don't need that. What would be the advantage of this? Well, you can pack the channels closer to each other. So the transmission could be the upper sideband transmission, or lower sideband transmission, or full carrier or double sideband. With this form, we're going to, that's the simplest thing because less complexity being used with the equipment and the design. With this form, the entire modulated carrier is transmitted at full constant power. It is used for AM broadcast radio stations, commercial radio stations, amateur radio stations. Well, there are certain bands that are reserved for upper sideband or lower sideband. There's a whole bunch of stuff happening there. I'll demonstrate that to you in the lab. It is used for AM broadcast, commercial radio, and aviation communications. Amplitude modulation is over a century old, so it's more than 100 years old. Way more than that. Well, not way, but yet the basic principles can help us to understand other forms of modulation, out of which some of the basic ones are amplitude modulation, AM, frequency modulation, and maybe a phase shift modulation. 3 different types. All right. Other forms. So AM is old, but the basic principles can also help us understand other forms of modulation, including digital modulation. Right? Now, crystal radios, if you Google that, the crystal radio, there are a bunch of people that are hobbyists and they can show you how to make a crystal radio. The name of the crystal radio comes from the earpiece. It's the crystal. See that kind of looks like this here, like an earpiece. It's called crystal earpiece because that's the way it's made. It does have high impedance and very high sensitivity, which means it doesn't load. You don't have to have enough puncture energy to make that thing go. And the crystal radio, it would have antenna, it would have some sort of a tank circuit to detect, or you can tune to whatever frequency. You can regulate the coil, and you can regulate the capacitor, and you can have the diode just to provide the nonlinearity and rectify things. And there's some, maybe here's a tone control, but you can actually have this without those. So the energy that antenna is going to pick up, the electromagnetic waves, is going to have enough energy. It could have, it will have considerably long wire. That energy that the antenna is going to pick up from the air is going to resonate with the tank circuit, is going to have enough power to actually make this one go. And you can put your ear, you can stick this one in your ear, and you can actually have a radio, AM radio. Well, the quality is going to be desirable. However, it's going to work. Without any batteries needed, no whatsoever, no power supply needed. It runs on the energy from the air. So, crystal radios were very popular at one time as AM radios, amplitude modulation radios, and are still popular with the hobbyists, the crystal radios. They do not require power and were used extensively during the World War II to receive broadcasts without being detected and without needing the power. Power from the actual carrier, power from the actual, because the carrier does a certain amount of power. The power of the carrier is enough to create the audio voltage right here. The current broadcast AM band is from 540 to 1700 kilohertz. However, the AM modulation can technically be used in any frequency band. What are some of these issues with using other bands? Well, it can interfere with other stations. So things have to be regulated. Well, there goes this slide. Come on. All right. Double-sided full carrier AM, double-sided full carrier transmitter. A mixer circuit with two sources, the carrier we talked about, and the intelligence signal pass through a nonlinear. That's the key. The device has to be nonlinear, or it has to have nonlinear capabilities, and transistor is just the thing to do. You have to be operating within the nonlinear region, because a nonlinear region will create the sidebands. The linear in the linear region here, you would not have the sidebands created. So you're gonna here is your window of opportunity, which is usually being used. Here's another window of opportunity, which is not that often used, if at all. So a mixer circuit with two sources, carrier and the intelligence signal, pass through a nonlinear device can produce AM signal at the carrier frequency. What happens if a tuner, the receiver, is tuned to the carrier frequency and there is no intelligence signal being transmitted. The microphone is silent. Well, you're going to, once you find that frequency, you're going to find silence. So all the noise is going to stop and boom, you found that channel. And if nobody is talking to the microphone, you're going to hear silence without the hiss and buzz of the noise. Okay. All right, a diode or a transistor are nonlinear devices. Well, there you go. Transistor can also produces gain. So hey, bonus, we can have an amplifier too. So a transistor also produces gain to drive an output to transmit directly, or with another amplifier. Only if you hear that somebody is using some packing tape in the background. Not shown is the biasing of the transistor to ensure, so not shown in the circuitry. This is just a concept diagram. And of course, all the biasing resistors and whatnot, they are not included in this diagram, but they have to be there in order for this thing to work. Not shown is the biasing of the transistor to ensure it operates in the nonlinear range shown on the graph right here. The carrier and the intelligence can be combined as shown or through a resistive network. Right here, this is quite primitive, but way of showing it. But in a nutshell, that's what it is. They can be combined this way or through a resistive network. Resistors, bunch of resistors connected parallel. I remember we would do this summing amplifier, for example, with the operation amplifier. And what do we have here? Over here, we have a tank circuit. Purpose of that tank circuit is for that to be tuned to the carrier frequency. So once we have that carrier frequency here, and it's going to go into the input of this amplifier or the transistor amplification device, let's call it an amplifier, then the tank circuit, if it's tuned to that carrier frequency, it's going to have a high it's going to resonate with the carrier, so the signal is going to go, whoa, it's going to skyrocket. It's going to go stronger. Which brings me to the next point. You could have the carrier, because what do we use to produce carrier? Well, an oscillator is an awesome device to produce carrier. You just have to manufacture or design and produce an oscillator. What kind of an oscillator? Well, how about an astable multivibrator, which basically you turn it on and that thing just goes. It oscillates. Astable, as opposed to monostable, for example. Multivibrator. Now, you could have that oscillator oscillating at a frequency that is lower than this tank circuit is tuned to. As long as it can produce a harmonic that this tank circuit can pick up, and boom, there you go. It just amplifies that. So there you go. So this oscillator carrier can have an oscillator producing not exactly the same frequency, but it can produce a lower frequency as long as it does have the harmonic, which can be picked up and amplified by the tank circuit right here. Did we go through everything here? Yeah. On the previous slide, okay, what do we have? The output is an actual modulated carrier. this carrier is going to be modulated by this intelligence signal, and that's going to be on the output. So this carrier modulated or affected by the intelligence is going to be on the output. In practice, it can be difficult to design modulators and filtering at higher frequencies, so intermediate frequency is used. Yeah, before we continue, I just want you to understand the concept of intermediate frequency. Let's say we have some sort of a receiver that has the intermediate frequency stage. And that can be supported with all kinds of electronics and well-adjusted system in order to produce a quality audio signal. Before, we have a tuner that tunes to the whatever carrier frequency I'm just going to call EC. And the frequency of the carrier could be different. Could be many carriers, could be many stations, many stations. Whatever it tunes to, it shoots that to another stage that converts by applying some other oscillators here. It converts that carrier frequency into one intermediate frequency. So whatever it is here, there could be many different frequencies. At this stage right here, things are going to be converted to one and the same frequency, based on which we can dress up the electronic components and we can make this a quality receiver, because we just have to adjust everything to that carrier. So that carrier is converted to another carrier, and that carrier is being processed. The word super heterodyne comes to mind. Okay. So let's just recap here. In practice, it's difficult because if we had a circuitry that has to accommodate all kinds of carriers, it would be difficult to accomplish. So the same approach is used to receivers from the demodulation. Okay. So it can be difficult to design modulators and filtering at the receiver on other transmitting stages as well. At the high frequencies, and many frequencies, so intermediate frequency is used. So that's the idea of the intermediate frequency here. The same approach is used for receivers to perform the demodulation. So the intermediate frequency is being produced for before the main carrier is introduced, and at this transmitting stage, and after the carrier is received in the receiving stage at the receiver. Just to make sure, because it's simpler to design a circuitry to process the signal with better quality. Common frequencies for the intermediate frequency are used 455 kilohertz, and another IF frequency that's commonly being used is 10.7 megahertz. It just so happens that this one here is being used with the AM radios, for example. And this frequency here is being used in the FM radio systems. Commercial. In the block diagram below, the oscillator would be a much lower frequency than the final carrier, And once the signal is modulated, it can be multiplied up in the frequency. That's what I explained to you with the tank circuitry. And so oscillators can be lower frequency, and the harmonics can be picked up by the tank circuit. Right here. So the oscillator could be lower frequency, as long as it has the harmonics. I'll have to repeat it for a third time. Okay. Now, yeah, so it could be those tank circuits can be tuned to 10 or 20 times the oscillator frequency and still get the harmonics, pick it up, and make use of those harmonics. IF amplifiers, this is not if, this is intermediate frequency. IF amplifiers and circuitry normally have very sharp band pass filter performance to ensure that modulated waveform can only contain components of the desired frequencies. Why do we need that? Because of this. Before the channel is being shot into the air, it goes through a bunch of filters, band pass filters. It has to go through a band pass filter in order to filter out whatever else it carries with you. I mean, with it, not with it. Why? It's because whatever else comes with it, if it were not filtered out, it could cause intermodulation problem. And it could affect other channels. And those, if they were not filtered out, they could affect those and the other ones. So things are being cleaned up and then shot into the air. So we don't have the intermodulation problem. And now there's a doorbell. Okay. All right, so let's say here, let's just analyze that a little bit, shall we? Here we have the intelligence microphone signal transducer. And we have the speech amplifier. So it'll be like an audio amplifier, audio processor limiter, and all the audio processing circuitry that goes. And look where it goes, right into the modulator or a mixer. Same thing. Then what we have the oscillator that oscillates, or the oscillation circuitry. We could have an oscillator and then tank circuit to amplify whatever we need to do. Goes through a buffer just to provide some sort of safety between those stages here. I don't know why they, well, let's say, okay, there's a buffer there. So the oscillating frequency, the oscillator, and the intelligence get to the modulator, which mixes things up. Then we have this frequency multiplier stage, which would be this here, for example. Then there's a driver. Well, driver is an amplifier that makes things, takes a smaller signal and makes it a little bigger, or a lot bigger. So there's the final amplifier. There's a driver that supports the amplifier. So here's a very low signal. Then this one boosts it up, dresses it up, makes it a little bit more meaty, and then shoots into the final amplifier. The final amplifier takes it and, whoa, let's make that thing really strong, filtered out. So there's no any additional things above and beyond. So they cannot, so they don't affect other channels. And boom, is being shot by the antenna into the air. And things have to be filtered out properly, and things have to be adjusted properly as to the frequencies, so there's no interference. And well, it's quite legal because industry Canada is quite strict with this. And whatever the industry, industrial quality control when it comes to the frequency spectrums in any other country in the world. They are quite strict. Double sideband, double with sugar. Double sideband of full carrier AM. Full carrier. In order to modulate the carrier with intelligent signal, we need to use a nonlinear, whatever. We already established that, sort of. The carrier and the intelligent signal are multiplied together. Multiplexed, maybe is maybe a better word, mixed together. So the modulated carrier contains all the information in the intelligence signal, or the information of the intelligence signal. In the figure below, here's the figure, because this is below and here's the figure. In the figure below, we can see the AM waveform is being varied at the same frequency as the intelligence signal. Here is the carrier. You see, the carrier is constant frequency and constant amplitude is being introduced into the mixing stage. And here's the signal. And if the signal gets stronger, then this thing gets modulated more. The carrier is modulated more as far as the strength of it. If the intelligence signal is weaker, then it's going to affect, as far as the power, it is going to affect, or strength is going to affect it less. So here's our reference signal. We crank up the volume of the music, then the carrier is going to be modulated more as far as the amplitude modulation. And if we crank up the volume less or uncrank the volume, then of course the carrier is going to be modulated less. And if there's a complete silence, then the carrier is going to be as it is here. And if the frequency changes, then this is going to change as well. So if this was a lower frequency, this would also be affected at a lower frequency. If it were a higher frequency, it would be affected. So here's a lower frequency, here's a higher frequency. So the frequency of that of the intelligence signal would carry the tone of the signal, higher tone or lower tone. And the strength of the signal is going to convey through the carrier the volume, loud or quiet. What we have here, in the figure below, we can vary it at the same frequency as the intelligence signal, okay? In such way that when the intelligence is at the maximum value, the AM waveform has a maximum peak-to-peak value. Yeah. And when the intelligence signal is at the minimum, the AM waveform, envelope, that's envelope here, waveform, has a minimum peak-to-peak value or variations. The AM waveform below is what we would see in the time domain on the oscilloscope. And it's important to note that it no longer includes the low frequency component. It's just that green line is just drawn here. But it is just the carrier that changes in certain way. So this statement here is half true, because technically it does, but it is, from another perspective, it's just that carrier frequency that's being transmitted, and it's being varied at the rate of the intelligence signal. In the figure, we can see that the amount of modulation is different. This is something we can call control. This is something we can control as part of the design. Does it matter? Okay, let's read that again. Here we can see the amount of modulation is different. Yeah. Stronger signal, more modulation, weaker signal, less modulation. This is something that we can control as part of the design. Does it matter? Of course it matters, because that's where we have the dynamics and the frequency. So volume and tone variations. Hey, we can transmit music or voice. And I'm going to point something to you as one of the building blocks for the future: modulation index. If we continue to increase the modulation, a situation known as overmodulation can result. Radio frequency interference. Okay. And distortion in the intelligence signal at the receiving end. So we can only modulate this thing so far. If we took too much, if we put too much signal here than the carrier can handle, then we're going to have clipping one way on the top. We're going to have the signal being lost on the bottom. So we can only have so much dynamics. Yeah. And the index of modulation can help us with this, If we continue, it is normally considered to be a fault condition, and if it's over modulation, it's a fault, and it will be in violation of users' license agreement by the industry Canada, for example, in Canada. Because if you overmodulate, then overmodulation can cause additional sidebands, which can interfere with other stations. So things are being controlled quite tightly here. In a figure of merit, known as the modulation index, using the symbol M, here's a formula for you to put on your sheet, is defined as the ratio of the intelligence amplitude to the carrier amplitude. So here's the amplitude of the intelligence signal divided by the amplitude of the carrier signal. And if you want to have that in the percentage, you just multiply it by 100 and you have the modulation index percentage. Note that the modulation index does not depend on the frequency of the modulating signal. It's just the strength of the signal. But it does depend on the voltage of the modulating signal. If the modulating signal is voice, the amount of modulation will be dependent on the magnitude of the voltage created by the voice at any instant of time. So that's why, just like in any audio systems, you need to you only have so much room to play with. And if somebody shouts to the microphone, well, they're not going to be heard louder in the speakers. They're just going to be heard more annoying in the speakers, because the sound, if you start clipping, there's going to start distorting the sound, and it's just going to sound ugly. So again, the frequency of that. Now, if you have more frequency when you're modulating AM, if you have more frequency, no, that's not what I want. If you have more frequency that the sidebands can handle, if the frequency is higher, at the final stage, the transmission undergoes through, or it goes through a filter. So those frequencies are just not going to be heard. That's why the music in the AM radio stations does not sound as clear because some of the higher frequencies are missing. So if you overshoot the frequencies, they're just not going to be heard in the transmission. But if you overshoot the volume, then you can cause some problems with the modulation here. So that's why the final stages of the amplification of the transmission systems are quite protected by limiters, filters, and so on. So the limiters would prevent the overmodulation amplitude-wise, and the band pass filters would prevent other frequencies to be present there. So other channels cannot be affected. So something that's called intermod or intermodulation. We don't want that. Okay. So here's the formula or formulae. Amplitude modulation graphic analysis. Okay, we can also use the graphic means to calculate the modulation index. And I'm just going to go over that kind of quicker, but I would encourage you later on to kind of analyze this. And this is what makes us slow readers. Because when it comes to things like electronics or subjects like that, sometimes you have to stare at the page and read it again, analyze it, look and get frustrated, and then, whoa, get a light bulb, get enlightened. Yeah, I got it. Okay. So I would just encourage you to kind of revisit that image once I post it, and concentrate on that, because it is going to be on one of the labs. I think it's going to be the next lab after that, amplitude modulation, that we're going to have. So we can also go, the modulated waveform has the minimum value at the W point, or the maximum value at the W. So here's the W and here's the W point right here. So the modulated waveform has a maximum value at this point, obviously, and it's going to have the minimum value of this point. The maximum value and the minimum value. Okay, got it. If the value goes to 0 as a result of an increase in the modulating signal, because you can increase that and it's just going to hit the bottom here, it can't go any further, right? Then we're going to cause something that's called overmodulation. So yes, you have to treat it with respect. I'm talking about the carrier. You can push it so far up and down, and it has to be symmetrical up and down here. You can only go so far here, and you can only go so far here. And over here is, by the way, this is twice as much as the carrier. Between here and here, here, twice as much as the carrier. All right, so the carrier will momentarily go to a 0 if you overmodulate it, resulting as a sideband splatter, resulting in and out of band emissions. No. It's going to try to go in and out of the bands here, which can create other sidebands, which can create, so that's why the limiters are at the final stage. All right, so here is the index, modulated index formula here. It's the strength or the value of the intelligence signal that we already established, that over the strength of the carrier signal times 100%, you get the percentage. Otherwise, you just get the ratio with no unit, of course. Or B minus A divided by B plus A times 100. Where's B? Where's A? Here's the same formula. Okay, so the B is, see here, that distance, that value between here and here, that's the B right here. And over here, A is this here value. There's certain names for that. I'll tell you later. The maximum value here, minimum value right here. If you apply this formula, you're also going to get a modulation index, which is used by, which will further we're going to apply this thing in practice. Example: calculate the percentage, the modulation index percentage with the 10 volt peak to peak. Don't forget that there's a 10 volt peak to peak here. Oops, laser carrier. So there's a 10 volt peak to peak carrier here. Calculate the modulation percentage with 10 volt peak to peak carrier with the following maximum and minimum peak to peak values. So here's a carrier, goes up 15 maximum and minimum 5. So here's 15, whatever units, let's say volts, millivolts, microvolts. And here's 5. Originally, this thing is 10 volts and it goes up to 10 and it goes down to 5. Apply that formula, you're going to get 50% modulation. Well, makes sense. Here is 10 volt. Sorry, let's say volts or millivolts. Well, that one is, we're talking about 10 volts, all right? 10 volts goes to 5, so 5 is half of 10, right? So it goes up 5 and down 5. It's modulated by 50%, which means we can go another 50% to make it 100% modulation. And of course, if it goes to 19 and 1, almost full. So that goes to 19 volts from 10 to 19, and from 10 to 1. We're pretty much almost using the whole thing here. Makes sense. And that is, if you apply that formula right here, that is going to give you 90% modulation. So we almost swung out from one end to the other. If it goes up to 20 and down to 0, up to full 20 and down to 0 here, then we have 100% modulation, which is maximum allowed. If we go any further, we're going to get overmodulation. And if you take a look at this, it goes from to 30 and 0. Yes, we kind of get the value of 100%, but it's 100% with the asterisks. Here. This is overmodulation. Very, very bad. Okay. Since the peak peak is more than twice the carrier, so we go further than we are allowed to. Further than the circuitry is going to let us through, which means if there's a sign, if there's a wave, it's going to get clipped here. If there was no limiters on the final stage, we would overmodulate and we would well, create some problems within the industry Canada. Now it goes to, now this one was kind of tricky, so I would encourage you to kind of like look at that line and analyze it, and I will try to explain as far as I can. It goes from 15 to 8. That means there's some sort of a DC element that's interfering with us. This will result in the distorted AM wave and distorted intelligence signal when demodulated, since the modulation is not symmetric. It goes up, it increases 5 and it just decreases 2 from. See, here's the thing. Where's that coming from? Where's that coming from? 15 and 8. Goes up to 15, so it goes up 5 from the resting point, and it only goes down 2. So you're going to have not symmetrical swing out from the resting point, which also is going to create a distorted wave. Once you do that IM modulation, if you have more time, I would encourage you to just, all you have to do is just increase the DC offset with some biasing stages. We can try to create that problem. Amplitude modulation in the frequency domain. All right, we talked about that already, but let's just analyze it again. When combining any two sine waves through a mixer, which is the combiner, to generate a product, the result will be the following. Well, we're going to come up with some sort of a DC level, hopefully not, but well, not the one that we don't want from the last example. So the DC level is going to be affected on the output stage of the amplifier or the mixer. We're going to have components, not electronic parts, but the components like a wave form or frequencies. That's what I mean by components. Components at the sum and the difference of the two original frequencies, which is most important, which is why I started this lesson that way. So again, we're combining two signals. We're going to have DC level affected, which we can filter out, no problem with a capacitor at the final stage. Not at the final, but at the output of the amplifier. We're going to have the presences of two original frequencies. Let's say, forget that. We have that 1000 hertz and 10 hertz. So we're going to have the 1000 hertz. And we're going to have the 10 hertz, which means that's basically these are the components of the two original frequencies. And components at the sum and at the difference of the two original frequencies. So here is the original frequency, or the original frequency is the carrier frequency. And there is the, let's say here, intelligence signal. So at the output, we're going to have this. We're going to have plus and minus. We're going to sum and the difference present on the output. And you see, because that we don't want that to be at the output. We're going to filter it out. We're just going to have a band filter. That filter just passes through from here to here and shoots it out. And we're going to have those harmonics. So see, that also has to be filtered out. That's why we use band filters before we shoot things out to the antenna. We want that to be filtered out. And we want that to be filtered out because there's going to be another channel somewhere here. And that other channel also is going to have their things filtered out, so that one doesn't affect us. Okay? Lower frequency is a difference, blah, blah, blah. Signal and the upper side frequency is the sum of the carrier. We talked about that. And the carrier is in the middle. There we go. It is important that the lower side frequency and the intelligence signal are widely separated, or we would have a form of mixing resulting in aliasing or fold-over distortion, one channel affecting the other. And if one is affecting the other, you're going to have something that's called a frequency beat, because we're going to have combination of those, and then those are going to combine with the other ones, and they're going to create another different side bands of their own, creating something that's called aliasing, which basically are going to produce things that are not supposed to be there. What it comes down to is we need to filter things out so we're not affecting anything else. And here's why. Amplitude modulated, okay, amplitude modulated sine wave in the time and frequency domains. So here's a time domain representation. Here's the time. Here's the amplitude, and here's badly drawn because almost like a. Imagine this thing is going up and down. So when we combine this here, that greened out area, that's a sine wave that is so thick that we can't even see the sine wave, but it's a very high frequency, condensed, so we can't even see the waveform. Combined with the intelligence, we're going to get something that is called a modulation envelope. And that's what you would see on the oscilloscopy, if you have this thing in the time domain. Now, when it comes to the frequency domain, FFT, we're going to see a spike of that carrier frequency. We're going to see a spike of the difference between those two frequencies, and we're going to see a spike of the sum of those two frequencies. And that's the only thing we want to see after filtering things out. If we don't filter things out, just connecting to oscilloscope, sorry, my sense of humor, then yes, you're going to see somewhere here off the screen, you're going to see just that the intelligence signal. And of course, we're going further down, you're going to see the harmonics of the carrier and harmonics of the sidebands. You're going to see harmonics of the intelligence signal as well, and the noise. But we need to filter things out. I can't say it. I can't say it enough. And when I was showing you at the very first slide, on the not even a slide. See here. If we have, if that's, if we just have the intelligence signal as a sine wave, that is, yeah, that's what we're going to see. That's going to be a spike. But if we transmit voice, The voice, look, so far we have considered a single frequency sine with a constant frequency and amplitude as the modulating signal. A voice signal is much more complex. A voice signal is not as simple as a sine wave, and it contains frequency components from approximately 200 hertz to 3 kilohertz, just a human voice. Forget the music, it's more, right? But just to transmit the voice, and if you want to transmit on that sideband, you won't make the person sound like that, okay? I just covered my nose. Right? So what do we have here on the left and on the right side of the carrier? Well, if there is a 3 kilohertz at some point in time, it could be just a glimpse, it could be just a momentary presence of 3 kilohertz, then we're going to have that spike and that spike. And if there's 200 hertz present, we're going to have that spike and that spike. And if we constantly have a lot of frequencies, because my voice contains a lot of different harmonics and a lot of different frequencies, then we're going to have anything between constantly, and it's not going to look like a rectangle. It is going to look like it's going to look like a mess to our human eye, but technically it's not a mess. It's proper signal. Okay. So that's why we call those sidebands. Lower sideband. Oh, it even says that here. Lower sideband, upper sideband. And between the far end of the lower sideband and the far end of the higher sideband, here we have the whole bandwidth. Then we could fit the intelligence. And the wider we make this, the better quality music we can transmit. The narrower we find that, lower quality of the sound. No, if it's just a voice, so you can communicate by voice, you can have many more channels. So it's a give and take. You pay for the space with the quality of the signal. Now, things are getting better, but just a few years ago, some of the call centers, like if you call, any of the product support or something like that, they would pack. They would try to maximize the bandwidth to have as many conversations, voice conversations as possible in their phone systems with the modulated signal, that quite often you would hear that you would have to ask people to repeat because the quality of the transmission would be questionable. Plus, the channels would start overlapping, and you would hear some aliasing in the form of maybe some kind of like somebody gargling water in the background. That would be the other channels trying to overlap, because the filtering was not as efficient as it should have been. Now, after so many years, well, not so many years, but after a few years, the technology improves. So you rarely have that kind of problem. But a few years ago, you would hear that more. That's what happens if you use a carrier of 1 megahertz modulated by 0.2 to 3 kilohertz signal. We get sidebands as below, and sideband goes from here to here. Okay, from here to here, from here to here, da 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 da. So that's basically what that thing says. The modulating signal does not have to be voice. It could be a data stream. That's why when the fax machines were introduced in the beginning of 90s, some of the phone systems, some of the phone lines were not ready for that because they would have the voice lines, well, pretty much packed with channels. The modulation would be so tight that the sidebands would not have enough frequency to carry the fax machine tones. So some of the fax machines would malfunction or the fax transmissions. So that was taken care of pretty quickly. Just a couple of years go by, and the circuitry was improved. Excuse me, talking for almost 2 hours now. And believe it or not, I'm not sure if you remember that not that long ago, the phone conversation would sound like that because of the narrow bandwidth that each channel on the modulation channels would have. Now you don't even realize that because you always get used to things that are better, quicker than the other way. Now you can hear who's talking to you. Before you would have to, okay, who's this? Oh, that's you. Okay, oh, let's meet for coffee or something. Yeah, because when you strip the harmonics, you just get the intelligence, you get the words, you hear the words, but it would be difficult sometimes to distinguish one person from another over the phone, for example. Radio communications, walkie-talkies, and all that stuff. That's also same, same thing. Okay. The modulating signal doesn't have to be voice. It could be a data stream. For various frequency bands used, there are specifications of the bandwidth. So whenever the system, if you're going to be designing a system, you gotta, if you get to that point, designing something like this, you just, of course, you're going to have to make sure to see what is the frequency bandwidth that is required for whatever type of transmission. So you're going to have to analyze the signal that needs to be carried. In the image above, the sidebands are shown as rectangular. What would they really look like on a spectrum analyzer if someone was speaking? Well, we already talked about it. It would just look like a constantly ever-changing, floating kind of a mess here. An example, 10 megahertz carrier is an amplitude modulated by a frequency shifting data. Okay. Signal that has a frequency components of 5 and 10 kilohertz. What's the range of frequencies of the upper and the lower sidebands? Okay. Well, what is the overall occupied bandwidth? All right. The USB upper sideband in this case is 10. Was 10 megahertz we have? Yeah, 10 megahertz, 10 and 6 zeros, plus that 2. So the carrier plus the 5 kilohertz. From there, 2 carrier plus 10 megahertz. So from here to here, that will be the upper side band. Or if you do the math, you're going to come up with these numbers. And then the lower sideband, you just do the subtraction. And if you put that against the carrier, you're going to get that number. If you put that against the carrier, you're going to end up with that number. And that's going to give you from here to here. And what's the overall bandwidth that's being used? Well, from here to here. Okay. And here is the overall 10. Okay. Well, you see here, 20 kilohertz. Far extreme of the higher frequency plus far extreme of the lower frequency of the higher frequency. Take this bigger number, swing it all the way that way, swing it all the way that way. Look at that, I get 20 kilohertz. That is needed to transmit whatever the data is that uses anywhere from 5 to 10 kilohertz. Simple, eh? Ooh, that's a black screen. Okay, that's as far as I want to take you today. And we're going to continue with some of those because I'm going to add a couple more screens. So I'm not going to post that until the lab, or maybe I should just post this, and then when I add the other slides that I'm going to show you during the, I'm going to take maybe half an hour from the lab, and then I'm going to take that off the content area and replace it with the slides that I took out for today's presentation. In the meantime, this is it for today. Welcome back from the reading week. I hope that wherever you went on the holidays, you spent all your money, and now you have to keep working, just as I have to keep working. It never stops. Thank you so much for your attention, and I'll see you when I see you.